Hello everyone, how are you? I hope all of you are doing good. So today is a next lecture of non-traditional machining method, and today we are going to cover this topic. Hardly we are going to cover this topic within a 30 minutes because most of the important topic of the non-traditional machining method we have covered in our previous class. Right. So let's start. So today the remaining topic which I am going to cover is what? Laser beam machining, electron beam machining, abrasive water jet machining, okay, or water jet machining. So these topics we are going to cover in today's session, right? So let's start. See, laser beam machine. My dear, in laser beam machining method, let's discuss some points. Right, in laser beam machining method, you have seen that light amplification, stimulation, emission, radiation are focused with the help of lens on a workpiece. Right. So high energy beam is focused on a workpiece. Right. So here direct laser beam against the surface of workpiece as in the laser welding. Similar thing we can use in a laser welding as well. Right. Successive pulse from laser gun, basically which you are giving the successive pulse of the laser gun get vaporize the metal. Even the metal is going to be melt, and it is also going to be what? Vaporize, right? So location of the laser beam controlled by the computer. Manually you cannot control the laser beam, right? And workpiece need not to be conductive. In our previous operation we have seen that, like ECM and EDM, we need a conductive workpiece, right? But in this process we don't need a conductive workpiece because the overall machining principle is based on the melting, right? On melting, right? So generally the cuts are taper if the length of the depth of the cut is what? Large. In laser beam machining, basically produces a large remelt zone, right? And here it can produce a hole up to of diameter 0.0005 mm. So here you can produce a very fine hole in laser beam machining. You can produce overall, you can say that you can produce a deep hole in laser beam machining, right? You can produce a deep hole in laser beam machining. So it is, so where we used, right, laser beam machining. Generally, you have seen that to produce a cooling hole, right, to produce a cooling hole in a blades in vanes for jet engines, right? So this is the application. This is the application of the laser beam machine. Now the electron beam machine. My dear, let me show you the electron beam machining first. In the electron beam machining, basically what we are going to do, there will be a container, right? There will be a container. In that container, there will be a tungsten, okay? There will be a tungsten filament of negative, right? And there is a workpiece. This is a workpiece, right? And here the workpiece is placed on a work table, right? So this is a work table. Here you can see, right? This is the work table. Now there will be a magnetic coil. There will be a magnetic coil. There will be a magnetic coil. This is a magnetic. This is a magnetic. The work of the magnetic coil is to apply the magnetic field so that we can control the direction of electron beam. Here the workpiece is what? Positive, right? So electric field, basically electric field is stabilized in between the tungsten filament and workpiece, and electron will emit. Free electron emit from the tungsten filament, and with the help of magnetic coil we focus the beam of electron onto the workpiece, right? And the kinetic energy of the electron get converted into what? The kinetic energy of the electron get converted into what? Get converted into the thermal energy. So the workpiece going to be what? Mid. One thing is very important though, is that here The atmosphere is what? Vacuum. We have to ensure that there will be a vacuum, right? There will be what? There will be a vacuum, right? Generally, electron beam machining, here the weld zone is very small. Okay, so it is obvious that heat affected zone is also very small. Here, these type of machining, like laser beam machining and electron beam, generally used in what? Generally used in electronic industry. So let me cover some point regarding to the electron beam. Here, workpiece placed in a vacuum chamber. As I told you, please always remember that workpiece, workpiece placed in vacuum chamber, vacuum chamber, right? So high voltage electron beam directed toward the workpiece. Energy of an electron beam melt, or you can say vaporizes selected region of the workpiece. Electron beam moved by the deflection coil. As I told you, that electron beam is going to be moved by what? Moved by the deflection coil. This is a similar process like electron welding. So this is the overall scenario. Now the plasma arc weld. In plasma arc welding, my dear, there will be a ionized gas. This is what? This is the ionized gas. First, this gas is ionized, right? The electron will come out from the electrode, and that electron, okay, hit the gas so that the gas become ionized. Now the ionized gas is focused onto the workpiece. So these ions, high energy ions, the ions which are moving toward the workpiece having a very high energy. Once the energy is going to be converted into what? Into the mechanical energy, right? So they will produce what? They will produce the heat. So here the overall concept is that plasma is what? Plasma is a stream of ionized gas. So this is a very important point. It is a stream of ionized gas. How can you get? I told you. Typically, temperature are very high. Same process, right, as plasma welding without filler. Torch movement controlled by the computer. Power requirement. Okay, here power requirement depend on the material being cut plus depth of the cut. How much kinetic energy is required, how much energy is required to move the plasma will depend on the workpiece which you are going to cut, right? Which you are going to cut. Now the chemical machining. Let me explain you the chemical machining. Suppose that this is my workpiece, right? Try to understand. Suppose that this is my workpiece. This is my workpiece. My workpiece. This is a workpiece, right? This is the now. Suppose that on that workpiece we have to do machining on a specific section, right? Having a very small depth like this. See, see, this section we want to machine. This section we want to machine with the help of some chemical. So what we do, the other faces we are going to protect with the chemical film. So this is a chemical film. The chemical film which being protected, which being protected by the chemical, where we don't want any machining action. This one. See, Now, hang this with the help of what? With the help of some wire, right? The help of some wire, right? With the help of some wire in chemical tank. So what is going to be happen? This is chemical protect. This is what? This is a chemical protect. This is chemical protecting layer. Protecting layer, right? Layer. This is chemical protect, right? So this surfaces will be protected, right? From the will be protected from the chemical. Now, when you dip this surfaces, when you dip this all surface in chemical, so what happen? This surface is going to be what? Dissolve in the chemical, right? Okay, without affecting the other surfaces, right? Now, here chemical are used to dissolve the material, right? Okay, here masks are used to control the attack. Most common use in generally here these cavity which we are going to be produce na, the cavity, the height of this cavity is shallow, right? This is a shallow cavity. So we produce a shallow cavity, right? Shallow cavity. So most commonly used in a circuit board and plates of a printing. Here the cavity is shallow. Here the cutting speed, that is what the dissolving rate is very slow, that is 0.0025 to 0.1 mm per minute, that is a very slow, right? Very slow. So this is a chemical machining. Now the water jet machining. My dear, in the water jet machining, a high pressure water jet is focused on the workpiece so that the workpiece get what? Get erode. So a narrow jet of water directed at a high pressure and velocity against the surface of workpiece. Here jet of water erode the surface of workpiece, right? Thereby cutting will take. So this jet is going to be controlled by, okay, computer, right? This jet is going to be controlled by compute. Next is abrasive jet machining. In abrasive jet machining, okay, that is what? That is a dry. Abrasive jet machining, that is what? That is what? Dry. So here we take some abrasive particle and that abrasive particle will move with the help of what? With the help of gas. Let me explain you abrasive jet machining. What we do in abrasive jet machining, there will be a container, right? This is a chamber. This is a chamber, and below that chamber, this is a nozzle, right? See, see, this is a nozzle, right? This is a nozzle. This is a nozzle. Now, there will be a two opening. There will be two opening, right? This is a opening one, and this is a opening two. From the first opening, first of all, we supply some abrasive particle, or you can simply say here we fill some abrasive particle. Here we simply supply some abrasive particle, right? This is abrasive particle, right? And then there will be a chamber, there will be an opening, and in that opening a high pressure gas, a high pressure gas. This is a high pressure. This is a high pressure gas, okay, is supplied. This is what? This is abrasive particle. This is abrasive particle. Abrasive. This is a mixing chamber. Mixing chamber. Now, when the high pressure gas will come out, the abrasive particle will comes at very high velocity, right? They will come at a very high velocity and it will strike to the workpiece. And what happen? The erosion will take, right? So a very narrow jet of gas and abrasive particle achieve a localized cutting, right? Localized cutting. It remove material through the eroding action. So here the material get removed by eroding action of a high velocity of abrasive gas. The gas is first compressed and mixed with the abrasive powder, okay, in a mixing chamber and passed through the outlet. So this is the overall process, my dear. In abrasive jet machine, there are some specifications, right? And the specification are the jet is controlled by the computer. Here the gas pressure is atmosphere. The velocity of the abrasive particle which are coming through the nozzle is 300 meter per second, and the dia of the nozzle is 1 point, okay, maximum is 1.25, right? And the type of abrasive we use is Al2O3 silicon carbide, right? The nozzle tool material is tungsten carbide, and here the life of the tungsten carbide, that is a nozzle material, is up to 30 hour, my dear, right? So in abrasive jet machining, there are some graphs which may be asked in your gate exam. This is your MRR versus your mix, right? This is your MRR versus thing ratio. Mixing ratio means what? In the container, we are mixing abrasive particle and gas. So this is a mixing ratio, right? My dear, if you increase the mixing ratio, MRR increase, but after some point, MRR get decreased, right? Next graph is MRR versus your MRR versus MRR versus your abrasive mass flow rate, right? If you increase the abrasive mass flow rate, the MRR get decreased but a slower rate, right? But a slower rate. Next is MRR versus nozzle tip distance. Nozzle tip distance. My dear, when you increase the nozzle tip distance from the surface, MRR initially increase. After some time, it is stable. Then after a time, it will, okay, MRR get decreased. So abrasive water, there is a next abrasive water jet machining, right? The next is abrasive water jet machining. This abrasive water jet cutting is used to much harder material. Water is not used directly to cut the material in pure. Instead of that, we basically instead water is used to accelerate the abrasive particle. Here, water is used to accelerate the abrasive particle, which do not do the cutting. Abrasive water jet machining. Here you can see the standard. Basically, here water is also coming. So we take a more stronger material at the tip of the nozzle. That is what? That is a premium composite carbide, right? So this is it. So your non-traditional machining method is completely covered, right? So tomorrow we are going to start new topic. Okay, thank you.